You are looking at a real model's attention, computed on my machine a few hours ago, not an artist's illustration. The sentence is, the animal did not cross the street because it was too tired. Every row is a word looking at other words. Find the row for the word it. One cell burns bright, and that cell is the column for animal. The model is pouring 85% of that word's attention onto animal and almost none onto street. It has decided mechanically what it refers to. By the end of this video, you will know exactly how that decision is computed, why the same trick made modern AI trainable at all, and why it is also the reason long prompts cost so much. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now, let us get into it. Start with the problem, because it grows straight out of the embeddings episode. We turned each token into an embedding, a point in a space of meaning. But a plain embedding is frozen. The word bank gets one fixed vector whether you sat on a riverbank or deposited a check at 1. Same word, opposite meanings, decided entirely by the neighbors. A frozen vector cannot capture that. We need a step that adjusts each word's vector in light of the words around it. That adjusting step is attention. It turns a word's generic meaning into its meaning here, in this sentence. Here is the whole idea in one sentence. Attention lets each token look at every other token and decide how much each one should influence its own meaning. The heat map you just saw is literally that decision, printed as a grid. Now let us open up how a word decides who to look at. For every token, the model computes 3 vectors, and the names are worth learning because you will hear them everywhere. A query, a key, and a value. Think of a library search. The query is what this token is looking for. The word it broadcasts a query that says, I am a pronoun hunting for the noun I stand in for. The key is what each token advertises about itself. Animal holds up a key saying, living noun here, excellent candidate. The model compares the query against every key, and each strong match becomes a high attention score. Then the value is the content that actually gets shared. The scores become weights, and the token pulls in a weighted blend of everyone's values. Mostly animals in our case. The result is a new vector for it that literally carries animal folded inside it. Words mixing their meanings into each other in proportion to relevance. That is the entire mechanism. And here's the part I love. That bright cell in our heat map was layer 3, head 10 of the model. Not a diagram of the theory, the actual weights. This is the code that produced it. 26 lines, 1 pip install any laptop. And I will be honest about one detail because honesty is the house style. A model has dozens of heads, and I search them for the one where it looks hardest at animal. That search itself teaches the real lesson. The other heads in the very same model are doing different jobs. In our own heat map, one bright cell links cross to street, a verb finding its object. Another links to tired. Grammar in one head, references in another, emphasis in a third. That is multi-head attention, and it is not a bolt-on, it is the design. The model runs many attention heads side by side, each with its own queries, keys, and values, each free to learn a different kind of relationship. Then, everything gets combined, so each word's meaning is updated by many relationships at once. The model is not reading your sentence one way. It is reading it a dozen ways simultaneously, and you have now seen 3 of those ways in one real screenshot. There is a second reason the 2017 paper that introduced this, attention is all you need, turned the field upside down, and it is about speed. Older systems read text one word at a time, each word waiting for the previous one, like reading through a straw. Attention compares all tokens against all tokens in one giant simultaneous operation. That is exactly the shape of work graphics chips devour, which is what made it possible to train on the whole internet, which is what made the giant models of episode 1 possible at all. The title turned out not to be arrogant. It was a receipt. But all against all has a price, and you've already met it. Look at the arithmetic. 10 tokens make 100 comparisons. 10,000 tokens make 100 million. Multiply your text by 100 and the work multiplies by 10,000. That is the quadratic scaling we promised to explain back in the context window episode, and it is exactly why the window has a hard, expensive ceiling, why long prompts genuinely cost more to run, and why a whole research field exists to make attention cheaper. The mechanism that makes the model brilliant is the same mechanism that makes long inputs costly. The strength and the limit are one thing. Here is your 10-minute experiment for today. Grab the heat map script from the repo below and change the sentence to one that is ambiguous in a way you choose. The trophy would not fit in the suitcase because it was too big. Rerun it and watch where it looks now. Then change big to small and run it once more. You will see the attention move with the meaning on your own screen, and no explanation on this channel will ever beat that. What you learned today, attention unfreezes embeddings by letting every token weigh every other token. The weighing runs on queries matched against keys pulling in values. Many heads read many relationships at once. The all-at-once design made modern scale possible, and its quadratic cost is the ceiling on your context window. You have now seen the full picture of what a model is and how it thinks. Next, the series turns practical. One free tool, Alama, puts one of these models on your own laptop, private and offline, and we will do it together and be honest about the trade-offs. That is next. That is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.